Well, we're breaking lesson 9.5 up into two parts again, looking at factoring difference of two squares, and in this video we're just going to factor binomials that are difference of two squares. Algebraically, if we have a squared minus b squared, it's the same as a plus b times a minus b, or a minus b, a plus b, we don't care which one comes first. Let's FOIL that out to show why it works. If I multiply a plus b times a minus b, I have a squared minus ab plus ab minus b squared, and the middle term drops out, so that's the same as a squared minus b squared. And then in the example there, they say x squared minus 9 is the same as x plus 3 times x minus 3, or x minus 3 times x plus 3, don't care which one's first again. So if we multiply that out, I don't know why I like to write the plus first, it just seems nice. Again, x squared minus 3x plus 3x minus 9. Middle terms drop out, so x squared minus 9. So anytime I have two things that are perfect squares with a minus between them, I can factor them using this factoring pattern. So this is going to be a pretty quick one. All I have to do to factor is see that I've got a binomial that has two perfect squares with a minus in between there. Square, square, minus, yep. So my factoring pattern says it's going to be m plus square root of 64 is 8, m minus 8. And if we want to, we can check, but this is what you'd probably do in your head. M squared minus 8m plus 8m minus 64. Oh, look, I got what I started with. So I know my answer was right. Okay, same thing. My greatest common factor is 1. I have two perfect squares with a minus between there, so it's going to be 4y plus 9z. 4y minus 9z. And to check, I could FOIL it out. I get 16y squared minus 36yz plus 36yz minus 81z squared. I know my answer is right, so I'm happy. I can see I have a greatest common factor of 3b this time, so when I factor that out, I'm going to have the 3 is gone, I have b squared minus 9 left. Okay, so I need to keep the 3b, but then I can factor the b squared minus 9 as b plus 3, b minus 3. If I multiply it back out, just doing my check step here, I'd have b squared minus 3b plus 3b minus 9. Middle terms cancel out. If we distribute the 3b, we'd have 3b cubed minus 27b, which is what I started with. So I know my answer is right, and we move on. Now it's getting more interesting, because first I can take out a greatest common factor. Then I have y to the 4th minus 625. Okay, I'm guessing 625 is probably a perfect square, because that's what we're doing this lesson. And I use my calculator, and lo and behold, it is. Square root of 625 is 25. So I have y squared plus 25, y squared minus 25. Okay. This is fully factored because it's got two squares, but that's a sum. It's a plus. This is still difference of two squares. So guess what? To get to fully factored form, I can do that one more time. So y plus 5, y minus 5. And there she is. Well, this one's different. It's not a binomial. Ooh, it has 4 terms. Ooh, we always look for first the greatest common factor. So in this case, it's going to be 6. So I have x cubed plus 5x squared minus 4x minus 20. Okay, greatest common factor found. Now I have 4 terms, so we go to factor by grouping is our method of choice with 4 terms. Greatest common factor of the first 2 terms is x squared, and then I have x plus 5. Next 2 terms, I could take out a 4, but I want to take out negative 4 because I know I want to get x plus 5. Negative 4x divided by negative 4 is x. Negative 20 by negative 4 is 5. And now the greatest common factor of the whole polynomial inside the parentheses there is x plus 5. So I have 6 times x plus 5 times x squared minus 4. Okay, that we've already done before. What's new is, oh look, I still have a difference of squares I can factor here. So I have 6x plus 5, x plus 2, x minus 2. And if we took the time, I'm not going to for the sake of time, we could multiply this whole thing back out and get what we started with. Our difference of squares factoring pattern is a squared minus b squared is the same as a plus b times a minus b. And sometimes it may be necessary to use more than one factoring technique or apply a factoring technique more than once in the same problem.